Welcome to This Explainer. Today, we're basically playing high-tech detectives. We're going to investigate exactly what causes catastrophic insulation failures in electric vehicle motors, and more importantly, how brilliant engineering works to prevent those failures from ever happening. If you're fascinated by the hidden physical limits of high-performance EVs, you are definitely in the right place. Here's our roadmap for today. First, we'll look at the root causes. Then, we'll dive into smart diagnostics. After that, we're engineering the shield, and finally, looking at real-world validation. Let's get right into it. Section 1. Root causes, or as I like to call it, the invisible threat. So, what actually kills a high-performance EV motor? It's a pretty fascinating question, right? Because before you get a massive high-voltage breakdown or a sudden catastrophic short circuit, there are these microscopic, totally invisible forces tearing the motor apart from the inside out. We aren't talking about a sudden snap here. We're talking about a slow, silent assassination of the motor's internal insulation. There are really 4 microscopic culprits at play here. First up, high electromagnetic stress. Modern EVs use silicon carbide inverters and they switch incredibly fast. We're talking rapid, aggressive voltage spikes. Second is thermal aging. Under extreme loads, internal temperatures can soar well over 130 to 150 degrees Celsius. That intense heat exponentially accelerates chemical degradation, basically baking the insulation until it loses all of its elasticity. Third, thermal mechanical abrasion. Just picture an EV in the dead of winter, going from minus 40 degrees to plus 150 degrees when it's running. The copper wire, the steel core, the resin, they all expand and contract at completely different rates, physically grinding against each other. And finally, electrochemical migration. If any moisture from, say, humidity or oily road salt breaches a seal, the high electric field pulls those contaminants in to create tiny, microscopic metallic bridges. We call them dendrites, and they act just like direct electrical shorts. Now, let's zero in on that electrical stress for a second, specifically a phenomenon known as partial discharge, or PD. Think of those extreme voltage spikes from the silicon carbide inverter, which can exceed 10 kilovolts per microsecond, by the way, as a high-frequency electrical hammer. This invisible hammer is just constantly smashing away at the first few turns of the copper wire inside the motor. When the local electric field gets a bit too strong, it literally rips electrons right out of the tiny air gaps. This generates ozone and high-energy sparks that viciously eat away at the polymer chains of the insulation, carbonizing it until it just fails. Moving on to Section 2, Smart Diagnostics, acting as the motor's vitals monitor. To detect these threats, the EV's software acts like a highly sensitive immune system. It isn't just sitting there waiting for the motor to break, it's actively listening. This brings us to active insulation monitoring, or IMD. The system is constantly pulsing the chassis ground with low-frequency signals. It's exactly like an early warning radar, calculating the high-voltage isolation resistance in real time. If that resistance dips under 100 kiloohms, which is about 500 ohms per volt, the system flags a level 1 warning. It knows for a fact that something inside the insulation is starting to degrade. But the absolutely crucial point here is this fatal threshold, 10 kiloohms. If the resistance plummets below this number, it means a severe breakdown is imminent. The system has to trigger an immediate severe fault interrupt to prevent a catastrophic short circuit, or worse, a literal explosion. Every single millisecond counts here. And because speed is literally everything in this scenario, we have KCL, or Kirchhoff's current law, leakage current monitoring. By constantly calculating the residual of the 3-phase currents, basically double-checking if what goes into the motor exactly equals what comes out, this algorithm can detect a tiny milliamp level leak to the ground and react in just 2 milliseconds. On top of that, there's a completely separate background software process looking for high-frequency electrical resonances. It's basically a canary in the coal mine, warning of degradation long before it reaches a critical level. All of this builds a brilliant 2-tiered safety fallback strategy. If the system senses light degradation, the motor enters a safe limp home mode. It cuts torque to 30%, limits your speed to under 40 kilometers per hour, and drops the switching frequency to physically cool the motor down and relieve that electrical stress. But if there's a severe breakdown, the response is incredibly aggressive. The system reacts in under 60 milliseconds, a window known as the fault-tolerant time interval. It executes a stepwise active short circuit, smoothly clamping runaway generated voltage below 720 volts, and instantly pops the high-voltage relays to disconnect the battery. It is a brilliant, fail-safe choreography. All right, Section 3, Engineering the shield, Let's look at the DNA and the vaccine. Now that we know how the motor dies and how the software catches it, let's step straight onto the factory floor. Engineers are essentially vaccinating the motor against these threats before it's even assembled. To fight off those electrical hammers we talked about earlier, they mandate corona-resistant wire laced with inorganic nano-oxide fillers. These act like microscopic armor against electron impacts. Then, they engineer the partial discharge threshold to have a massive safety margin, at least 1.5 times the maximum voltage, even at 150 degrees. They use triple-layer Nomex Mylar Nomex sandwich liners inside the motor slots. And to protect against those nasty silicon carbide inverter spikes, they use physical LC filters that literally crush those deadly voltage slopes, dropping them from 10 kilovolts per microsecond all the way down to a very manageable 1.5. The assembly line itself is hyper-controlled. Every single step matters. First up, precision needle winding keeps the wire tension controlled to within a single newton, just so the delicate insulation isn't scratched during winding. After resin injection, they run 100% online partial discharge testing, firing 2.5 kilovolt surges down the line to detect microscopic flaws as tiny as 10 picocoulombs. Finally, the entire motor is sealed with high-tech fluoroelastomer O-rings and checked with helium gas to guarantee a leak rate of less than 10 to the negative 5 millibars per liter per second. It is, for all intents and purposes, an absolute fortress against water and salt. I really want to highlight step 2 from that process, vacuum pressure impregnation, or VPI. This is just incredible engineering. Think of this step as literally sucking the air out of the motor's lungs. They drop the pressure all the way down to 10 millibars to completely evacuate every single tiny pocket of air in the wiring. Then they slam it with 6 bars of positive pressure, forcing protective liquid resin into every microscopic crack. The result? There is absolutely zero airspace left for a partial discharge spark to ignite. And just to be completely sure, they verify this solid block of wiring with high-end 3D CT scans. Which brings us to Section 4, Real-World Validation, the proving ground. Before these motors ever hit the highway, they have to survive the most brutal torture tests imaginable. The sheer punishment they endure to guarantee your safety is honestly staggering. Take a look at the environmental test. They shake the motor violently on 3 axes, cycling it from -40 to plus 150 degrees Celsius, all while hammering it with 10 kilovolt per microsecond electrical spikes for 1,000 hours straight. The passing criteria? Zero carbonization. None. Then there's the IP69K test, where it has to survive 96 hours of salt spray and high-pressure hot water blasts, all while maintaining a massive 100 megaohms of electrical resistance. And perhaps the most terrifying test of all, the hardware-in-the-loop fault injection. They run the motor at a screaming 12,000 RPM under full load and intentionally inject a catastrophic 5 kiloohm electrical fault. To pass, the software has to instantly recognize the disaster and clamp the voltage safely below 720 volts in under 60 milliseconds. To wrap up our explainer today, I want to leave you with this somewhat provocative thought. As amazing as these physical defenses and software fallbacks are, the frontier is still moving forward. By using those early warning electrical resonances we covered earlier, engineers are gathering massive amounts of data. We might just be on the verge of training AI models to foresee these microscopic, invisible failures before a single spark even flies. Imagine predicting the exact moment an EV motor needs service, completely non-intrusively. It's an absolutely fascinating future for automotive engineering. Thanks so much for diving deep into the anatomy of an EV motor failure with me today, and hey, keep asking the big questions.